Today we're talking about graph machine learning. It's a field that's all about understanding the incredibly complex connections that are hidden inside our data.
You know, modern AI is fantastic at analyzing data that's neatly structured. It sees an image as a simple grid of pixels, or it reads text as a sequence of words. But so much of the world's data just doesn't work like that. It's relational, it's made up of things and the messy web of connections between them. And this is where a lot of standard AI methods start to struggle.
And that's exactly where graphs come in. Think of a graph as a universal language for describing and analyzing things based on their relationships and interactions. It's really the most natural way to represent this kind of relational data.
Once you start to view the world through this lens of graphs, you begin to see these network structures pop up in all sorts of unexpected places.
For instance, entire economic systems can be seen as giant graphs. You have companies and banks as the individual points, or nodes, and all the transactions and relationships between them are the connections.
We can also zoom way down to the microscopic level. A molecule is essentially a graph. Each atom is a node, and the chemical bonds that hold them together are the edges.
And here's an example we're all familiar with: social networks. On these platforms, people are the nodes, and they're all connected by friendships, by who they follow, or by other interactions.
Even the digital world itself, from the whole internet down to a single office network, is built on a graph structure. It's just a massive network of interconnected computers and devices.
So, we can see how graphs represent the world. But what can machine learning actually do with them? Well, it turns out there are three main kinds of predictive tasks.
These tasks basically operate at different zoom levels on the graph. We can make predictions about a single point, or node. We can predict a connection between two nodes, or we can predict something about the entire graph as a whole.
Let's start with node-level prediction. The whole goal here is to figure out a property of one single entity in the network. The model doesn't just look at that one node in isolation. It also looks at its neighbors and its local connections to help make a much more informed prediction.
A really amazing application of this is in biology, specifically with predicting the 3D structure of proteins. DeepMind's AlphaFold model is the famous example here.
In this model, every amino acid in a protein is treated as a node in a graph. The task for the AI is to predict the exact 3D coordinates for every single one of those nodes. And as you can see here, the computer's prediction is incredibly close to the actual structure that was verified in a lab. It's just a remarkable result.
We can actually measure this accuracy. For this particular protein, the model got a global distance test score, or GDT, of 93.3. You can think of GDT as the percentage of the protein that's folded correctly. Any score over 90 is considered just as good as experimental methods, which is just an incredible level of precision.
And the real-world impact of this work has been absolutely profound, contributing to a Nobel Prize in Chemistry for the scientists who led these efforts. It really shows how significant graph machine learning has become.
Okay, the second category is link-level prediction. Now, instead of focusing on the individual nodes, we're shifting our attention to the connections between them. The goal is to predict if a link is missing or if one might form in the future. This is the technology that powers recommender systems on sites like Pinterest or Amazon. What they're doing is predicting a probable link, a connection, between you, a user node, and a product node that you might like.
But this can be used for much more critical applications too, like in medicine, where it can be used to predict harmful interactions between different drugs. This is framed as a link prediction problem. Is there a potentially dangerous connection between two different drug nodes?
For example, a graph model predicted a previously unknown harmful interaction between two drugs, atravastin and amlodipine, suggesting it could cause muscle inflammation. And that prediction, made by the model, was later confirmed with evidence from actual medical case reports.
The third and final task is graph-level prediction. This is where we zoom all the way out and make a prediction about a property of the entire network. The model learns to spot global patterns across the whole structure in order to classify it. This approach is huge in drug discovery. An entire molecule is represented as a graph, and the model predicts if that whole structure has a certain property, like whether it could be an effective antibiotic.
It's a similar idea with traffic forecasting apps. They model a city's road system as one big graph. The system then predicts graph-level properties, like overall traffic congestion, which allows it to generate those accurate travel time estimates.
So, to wrap up, let's quickly summarize these three core capabilities.
So to review, graph machine learning operates on three levels:
First, at the node level, it predicts properties of single entities, which we saw with protein folding. Second, at the link level, it predicts the connections between those entities, which is what drives recommender systems and helps find drug interactions. And finally, at the graph level, it analyzes entire networks, which is essential for things like drug discovery and traffic forecasting. By modeling the natural relational structure of data, these methods give us powerful predictive tools across a whole range of fields.